This is problem 4-16, it's on page 197. During some actual expansion and compression processes in piston cylinder devices, the gases have been observed to satisfy the relationship, polytropic relationship, PV to the N equals C, where N and C are constants. Calculate the work done when a gas expands from 350 kilopascals, 0.03 cubic meters, to a final volume of 0.2 cubic meters for the case of N equal 1.5. Now, in the solution that I'll post for you guys after you turn in your homework, I went through and I actually integrated the boundary work, because really the equation they've given us, PV to the N equals C, could be rearranged so that you write the pressure, let's see, in terms of the volume. It would be V to the negative NC. Does everybody know how to do that with exponents? Basically, you're just dividing both sides by V to the N. Okay, so this is really pressure as a function of volume. That's really what you've got. CV to the negative N. Okay, so you can plug that into the boundary work equation, which says the boundary work is the integral of PV. So there's a function of P in terms of V. You plug it in, do the integration. Guess what you come out with? Go back one page to page 195. Which of the boundary work equations that's already integrated do you think you'd come out with? Number three, the polytropic process, right? The way that equation goes is like this. The boundary work is P2 V2 less P1 V1 over 1 minus N. Okay, so the boundary work evaluating from this equation is pretty straightforward. The only problem is, you notice you've got what? You've got N equals 1.5, P1 is 350 kilopascals, you've got V1 0.03 cubic meters, and you've got V2 equals 0.2 cubic meters, but you don't have P2. That's a very good question mark. Okay? So the only thing we lack in order to solve this problem is what's the pressure in state 2? Well, here you have to go back to this idea. If PV to the N is a constant, then that means P1 V1 to the N equals P2 V2 to the N. It's just a constant. Okay? So you can calculate P2, just rearrange this equation. It would be P1 V1 over V2 quantity to the N. I'll try to slow down so my handwriting's a little better. There. You see what I did there? I divided by V2. Since they both have the same exponent, I can pull that exponent out. Okay? So now let's calculate the pressure in state 2. So 350 kilopascals multiplied by V1, 0.03, over V2, 0.2, to the 1.5 power would give us the pressure in state 2. Now, I think I did this right. When I calculated it, I came out with about 20.333 kilopascals. So now we have the pressure in state 2. Okay? So we can calculate the boundary work, just P3, 20.333, and the units are kilopascals, multiplied by V2, which is 0.2 cubic meters. Subtract off P1 V1, 350 kilopascals, and V1 is 0.03 cubic meters, divided by 1 minus 1.5. Now, what is a kilopascal times a cubic meter? It's kilojoule, that's right. So this is boundary work in kilojoules, which is a measure of what? Power or energy? Something else. Energy, right? It's not an energy rate, it's an energy. Anyway, plug in all that in your calculator, you get 12.87 kilojoules of boundary work. Okay? Any questions on it? I see frowns and confused look and furious writing. Don't erase that yet, please.
Sure, it'll make the second time on the watch tonight.
Okay.